Welcome. We have over 100 participants already joining us. This is very exciting. I wanted to welcome everyone to the Nanotechnology Research Panel. This is hosted and presented by the Student Advisory Council of Future Problem Solving. Just a brief introduction. I'm April Mickley. I am the Executive Director, and it is truly my honor to work with such amazing students who are truly the driving force and leaders behind this webinar. We have some very brief community expectations just to let everyone know that this event is being recorded. We had some participants that signed up for the session and may not have been able to attend, so we will be providing recordings to everyone who did attend or even was unable to attend. Please use the chat or the Q&A feature for follow-up or new questions to the speakers. We will be watching those and making sure we ask as many of those as possible. The student moderators will be combining questions that are similar so that we try to ask different questions every time and not repeat the same question over and over. We do ask our attendees on the call to ask questions related to the topic of nanotechnology. If you have other general questions about different steps of the future problem solving process or other topics, please email your local program or you can email headquarters. Okay, I turn the program over to our student advisory group.
Hi, everybody. My name is Vedika Himani, and I'm the Executive Director of the Student Advisory Council. And on behalf of us, we're thrilled to host this event and so excited to see everyone here. We at the Student Advisory Council work to support problem solvers around the world through resources like these amazing panels, our research materials, newsletters, guides, and a lot more.
Hi, I'm Mahi. I'm the Vice Executive Director of the Student Advisory Council. Yeah, please stick around at the end. We're super excited for you to be here. Stick around at the end to learn how to get involved. We'll talk a little bit more about the Student Advisory Council. But for now, we'll turn it over to Cyrus, Trevor, Brienne, our amazing research directors here to get started.
Thank you for the kind introduction. I'm super excited to welcome everybody in attendance today and kick off today's panel on the affiliable topic of nanotechnology. So just to introduce myself, I'm Cyrus. I'm a co-director of research here at the Student Advisory Council.
Hi, everyone. My name is Trevor. I'm another research director for the Student Advisory Council. Brianne, I think you're on mute.
My bad. Hi, my name is Brienne, and I'm another one of the research directors from the Student Advisory Council.
So for those of you who are brand new to the topic of nanotechnology, here's just a brief overview of the topic.
So nanotechnology is a rapidly evolving field that manipulates materials at the atomic and molecular scale with structures typically less than 100 nanometers in size. This technology has revolutionized industries ranging from medicine and energy to electronics, textiles, and environmental science. By enabling precise control over matter, nanotechnology has led to groundbreaking advancements such as nanomedicine for targeted drug delivery, ultra-thin materials for antibiotic resistance, and nanodiamonds for temperature-regulating fabrics. However, as nanotechnology becomes more integrated into everyday life, it also presents challenges including potential health risks for inhaling nanoparticles and concerns over security and privacy. As researchers continue to develop new applications, it is essential to consider both the benefits and potential unintended consequences of nanotechnology to ensure its safe and equitable use across all sectors of society. And a major underlying question of this topic is how might the use of nanotechnology in medicine, healthcare, and other industries affect humanity in the future? On behalf of the Future Problem Solving program, I'm honored and excited to introduce our three panelists for today, Dr. Dylan Sherman, Dr. Ilse Nava-Medina, Dr. Vignesh Athiyarath. Thank you all for taking the time out of your busy schedules to talk to us today. These panelists will be discussing their experiences, expertise, and research with nanotechnology and the future of the field.
So we've reviewed the questions that you all submitted and have compiled a list for a question and answer session. If any new questions arise during the session, feel free to put them into the Q&A function on Zoom, and we'll try to answer them if time allows.
And before we begin with the Q&A, let's just give each of the speakers a brief opportunity to introduce themselves in order listed on the screen. So Dr. Dylan Sherman, if you wouldn't mind sharing a bit about yourself.
Absolutely. Thank you, Cyrus, and thank you everyone on the committee. Great to be here and great to see so many familiar faces on the attendees list today. I'm very much excited to talk about an area that's a big part of my life. Certainly been the primary work that I've done for the last 4 years as I've been completing a PhD over in the UK at Oxford. So nanomaterials, a very big topic. I'm not going to delve into what I researched right now, but I'm sure as questions arise throughout it, I can give a little bit more of an insight into the different areas of research that I've done. But just on the side, I guess for reference and context, I've also worked in law, practiced law, and now sort of consulting in management areas. So hopefully I can bring in a little bit of thoughts about regulation, some of the positives and negatives around how we think about the ethics and the management and commerciality as well of nanotechnology, and weave all that in throughout discussing the technical aspects too. But looking forward to speaking to you all and working with our other two panelists today.
Hello, everyone. It's a pleasure to be here, and thank you for the invitation. My name is Ilse Nava-Medina. My background is in chemistry and material science and engineering. I have worked both in research and nowadays working in my own startup. So I have, I'm happy to share the different insights for innovation as well. I'm very excited to interact with the students. Thank you.
Hi, I'm Vignesh Athiyarath. During PhD, I was mainly focused on supramolecular chemistry. So I use mainly the crystal engineering principles and also the non-covalent interactions between molecules to decide and dictate how the molecules arrange and pack in solid state so that we can evolve some new properties from these materials. So, and when I joined as a postdoctoral research associate at CUNY Advanced Science Research Center. Currently, I'm a postdoc here. So I joined in the Nano Science initiative, and now I am able to appreciate more about nanotechnology. So we have different fields of in nanotechnology we are having. So I am working based on peptides, and I also collaborate with others, mainly who are focused on material science. So I'm trying to bring some concepts of supramolecular chemistry to nanotechnology for applications. So I'm like loving this field, and I think in future also I'll be working in this field to understand more details in the field and use it for day-to-day applications. Thank you very much.
Okay, thank you all for the introductions. So without further ado, let's jump into the Q&A session. So our first question is just a general one. We'd like to just get to know the panel just a little bit more. So we're interested in what inspired you to enter this field and what has kept you engaged with it.
Well, I'm happy to kick us off. I think for me, the switch into nanoscience came after spending a year or two in larger scale materials research in chemistry. And I was researching things that are basically like sponges, but at a bit of a smaller scale. So we use them to absorb and desorb certain materials. Technically, the material is called a metal organic framework, but we'll kind of leave the precise chemistry nuances of that to one side. And these things, these big structures, they kind of look like supporting structures that you'd see around buildings that are being constructed. They have huge cavities, porous cavities inside, which we can use to take things in and out of. So they were used a lot for the sort of storage of hydrogen, to compress hydrogen in a particular space. They were used to capture carbon and release carbon. And then they started to be used for things like drug delivery. So taking in a drug into the open space and then releasing it later on when it reaches a site within the body. We found, though, in the most recent years that there's a huge benefit into reducing these materials down to the nanoscale. And there's two reasons behind that. When you take something that's sort of a bit larger and reduce it down to the nano level, you can expose a huge amount of surface area. I think like a cube, you know, a cheese cube in your kitchen. You cut it in half, you've got more surface area because you've cut it in half. You cut it again and you expose more surface area. And you can keep cutting and cutting and cutting until you have tiny little cubes. And the smallest cubes will have the most amount of surface area accessible on the outside of the material. So we took the same approach to our materials here and said, well, if we can cut them down and reduce them to a nano scale, then we can have a huge amount of surface area exposed on the exterior of our materials. And by doing so, we can maximize the amount of space that external things can interact with that material. So resultingly, we're starting to able to look at the idea of improving the ability to absorb or desorb certain materials because of that open expanded area, and also a chance for more likelihood of external things to interact with that material and react in certain ways. So for me, I think what inspired it was that it unlocked a whole new world of design, a whole new world of sort of function in the material that you couldn't achieve when you were looking at it at the larger scale. It's also just absolutely, you know, enjoyable and so much fun to keep looking at things that you can't see in the real world and uncovering a lot that is really invisible when you do a lot of science. And there's a lot of weird and wacky fundamentals that change down at the nanoscale. Things don't move and operate and sort of walk back and forth in the way that they do when we as humans walk around, primarily because of something called quantum effects. And those sort of really twist the way we think things operate at the small scale. And that leads to some sort of fascinating phenomena when it comes to the way light is emitted and transformed, which is something hopefully maybe I can talk about a little bit more. But for me, it's curiosity and then huge amounts of benefits that it can add to the research that I did before.
I can go now. So when I was starting my PhD, I joined one of the projects that was around like building nanoparticles that just sparked the interest. In that case, we were making nanoparticles that were not spherical, which was like it was a first for me. Most of the a lot of the times particles are like just spheres, and so these was like two-dimensional particles in the form of a hexagon. And so the way that these particles like increase the surface area of the material really enhance like the properties that we were aiming for. And so it was a good combination in my professional career for like combining the chemistry with the ability to manipulate the property of the material. And so the purpose for this was like as drug delivery materials that could keep some drugs in between. And so that was like the beginning of the interest in nanotechnology per se. And part of that also like understanding how the 3D structure, the macrostructure, behaves depending on the changes that you do with the chemical structure, just put a lot of influence into my PhD dissertation when I was doing biomimetic models where the microstructure was really a key component of the diffusion of the reaction that was happening in these models. And so I continue to keep that focus and motivation for like understand, really knowing that if you make a subtle change in the structure, it might affect greatly and positively the property of the material. And so my PhD dissertation working with biomimetic models, and now then for the postdoc, I work with creating polymers that are bio-inspired. But all of these manipulation, again, was very relying a lot on how the molecular structure was at first and what are the amino acids, the sugars, etc. And so what is the property that you obtain at the end based on these manipulations. So yeah, I really like nanotechnology because it combines like the micro manipulation and nano manipulation, but then you're able to see and to have an engineering approach to the properties and applications that you foresee.
Yeah, my answer is also very closely related to what Ilse and Dylan explained. So when I was doing PhD, I mainly focused on modifying the molecules so that we can decide how the molecules arrange in space, especially in crystals. So basically the organic molecules. So when I was doing that, I got very interested in how the molecules arrange, and particular arrangement, what the arrangement can result in the bulk properties. So how the structure of a particular packing of molecules can dictate the properties of that overall material. So recently, when I started appreciating the nanotechnology as a postdoc, now what I am focusing is that using small stimuli, whether we'll be able to change the overall packing of the molecule itself without destroying it. Overall packing, if you are able to tune it slightly, using some stimuli, so then we will be able to get tunable materials. So the properties of those kind of materials can be easily tuned to whatever we need. So it is very interesting to see at molecular level different interactions when we bring in, and different molecules which we bring in, they can collectively work together to make drastic changes to the overall properties. So I think that's what my interest, going deep into the materials, uh, atomic level or molecular level interactions, and correlating that with the overall property, and just trying to imagine a property and try to make molecules suitable for that, making them arrange suitable for that. So that's my main interest in this field.
Thank you. So our next question is, what are some of the most substantial developments that you've seen recently in the field of nanotechnology and in your work? And how do you foresee these developments impacting the industry as a whole moving forward?
Yeah, I can start on that. So the one of the important current fields which I appreciate is that nano reactors and nanoscience. So there are, if you talk about the current research in nanotechnology, we have several things to talk about. So I got interested in this because we are mimicking the bio, like an enzymes, the biomolecules like enzymes, in laboratory scale to do something which is not possible otherwise. So this will help actually uh, to make some materials which are very cost effective, and also we can eradicate the pollution effects and lot of health hazards, etc. And also energy efficient materials. This is also very important field which we are trying to look at. I will give you as an example. For example, water can do a lot of things at molecular level. So if you have material which is all having at the molecular level, if you have some water molecules inside, if you take out the water molecules and if you pump in the water molecules, the whole property will change. For example, it can expand and contract, and some materials can change their color, change their emission. So, and also they can also perform some kind of chemical reactions inside. So, these are very important for the future, because, for example, we can develop this technology to materials uh, to have renewable energy harvest. For example, every day, every time we are breathing, inhaling, exhaling. So when you inhale, you can see at this part, the humidity will reduce. When you exhale, the humidity is going to increase. So there are, if you imagine about a material which is installed somewhere here, whenever you exhale and inhale, the humidity change can be used to develop some mechanical changes, and these mechanical changes can be converted to electrical energy generation. So whenever you breathe, a material can generate electricity. So what will happen? You can store that energy easily, no? So in future you don't need to spend more the non-renewable source of energy. You don't have to spend. So this is what the current aspects of technology I like in nanoscience.
I'm happy to expand on a few other thoughts here. One interesting sort of area of development, and then also maybe pulling it back to a few more fundamentals about the industry as a whole. Let me start with an application. So I have a huge passion for things called quantum dots. They won a Nobel Prize, I think back in 2023. And I wasn't related to that, by the way. It was huge genius scientists around the world doing that. But quantum dots are a phenomenal piece of technology. You think of something that emits light. Imagine bioluminescent plants or anything like that out in the world, things that take in energy and then emit it at a different light than maybe what it absorbs in terms of color. Quantum dots are these quite incredible sort of nanoparticles where, depending on the size of the particle, you can change the color of light that it emits. And this goes back to a point I mentioned a few minutes ago about quantum effects and how there's this really sort of unusual physics that takes place at such a small scale. So quantum dots are these new kind of technologies that can emit light in quite a low energy fashion, and then we think they may be better than things like organic light emitting diodes, things called OLEDs that you might have heard being advertised in different TVs and various other devices. So quantum dots are a really, really exciting technology when it comes to energy efficient lighting. And it's an area I kind of started to try to apply some of our materials to a little bit later on in the research that I was doing. More fundamentally, though, I think nanotechnology is a very difficult area to research because things are at such a small scale. You often need a large amount of energy to observe and analyze your materials that you're designing. Sometimes that's taking it to a thing called a synchrotron, which uses massive amounts of energy to be able to sort of allow us to image things at a very, very small scale. Given they're so small as well, our materials are often quite brittle and difficult to analyze. So I think one of the big developments starting to influence research generally, but especially things like nanotechnologies, are ways that are less energy intensive to be able to observe things and measure our technologies. And importantly, starting to use artificial intelligence and modeling. At least in my field, we're getting to the point where we can start to model and predict and start to understand what materials might look like in ways that we just couldn't 5 or 10 years ago. And that saves us a huge amount of time and energy in the lab to create, synthesize, and characterize different nanomaterials. Of course, when you have more computing power, so there are these centers called exascale computers, which are these huge, powerful centers for computing that are starting to be developed in a few different areas around the world, Edinburgh, a couple of places in the US. And at that scale of computing power, you can run simulations and models over and over again to sort of optimize a system before you then look at trying to produce it in the lab. So I think computing power, modeling, and AI is a huge technology that will start to intervene and I think expedite a lot of nanotechnology research in the near future.
Yeah, I agree with that. Bringing on the AI, I know like that is probably a question that is being asked in general. That the fact that you're if you're able to save some time on the experiments and regarding a project, that's always like very valuable in terms of equipment, personnel, like the people that are gonna do the experiments, and to have like a better prediction for how a system might work. And you can also agreeing with like Dylan on like the instrumentation that comes with like these new discoveries. Like if you see nowadays, like recent novels have been awarded to the characterization alone, not just on the matter discoveries. So I think like having good tools that are going to help us like continue like seeing these nanotechnology discoveries are very important as well, and they should go like in parallel to have more on this understanding overall. But the other factor that I will say is like the sustainability. I know like at the beginning you guys posed the question around like how the healthcare effects for like the nanotechnology. We all are getting a lot of like messages like on the media, etc., like oh microplastics and many side effects with the personal care products. Like, and I can speak around that because I some of my area of research is the skincare, but the personal care products like the laundry detergent, many of these effective detergents are coming with nanoparticles or microparticles. But I think nowadays, there is more and more push for like sustainable solutions while still keeping the nanotechnology. So I think that's also another important piece of innovation to keep to pay attention to, so that the technology is sustainable and not just like one set of discoveries that is giving a boom, but rather like designing materials that are good for the long run.
Okay, thank you all for your insights. Our next question is one that several students were wondering about, and that is, what are some common misconceptions people have about the field of nanotechnology? And this can also be misconceptions that you all had too when you're first entering the field.
Maybe I can start. Maybe I think the most seen misconception is that nanotechnology is a very new field of science. Actually, which is not true. We can see in nature also. We can see in nanoparticles many places. Even the dust which you see. What is the dimension of the dust? And also, if you see the carbon, when you heat something, if you char something, even when the volcano erupts, the emissions of these kind of processes, the emissions, actually the dimensions of those kind of materials are close to nano scale. And another misconception is that people start thinking about some materials and the source of the nanomaterial, and they start correlating the properties. For example, we all wear the gold ornaments, and we assume that, okay, gold is not going to have any harm to your body. What happens if you make into a nanoparticle, gold nanoparticle? Some people think that, okay, yeah, this is the same as gold, so I can touch it. Nothing's going to happen, but it's not the case. The properties are entirely different when you go to the small scale. It can cause toxic effect in your skin. So I think this is the main misconception.
I will say the one in my case, I still like, or throughout the career, I realized, or I've been learning more about it. Is like the shape of the particles, nanoparticle, like the carbon nanotubes. It's a hollow tube. Nanosphere, it can be a hollow. A hollow nanosphere. The ones that I was working with, like they were hexagonal nanoparticles that increase the surface area, because that's how like the bees do the bee, like a beehive, like that increases the surface area. So and there are rods that are like Janus particles, which is one side is going to have a sphere and the other is going to be flat. And because of this difference in the shape, you're able to drive certain phenomena. So like just knowing that the shape plays such a big role as well, it was very it has been very interesting to learn like throughout the years.
Yeah, I might build onto that idea. Of course, because there's different dimensions, you can have nano in a different element. So you can have nano in X, Y, or Z. So sometimes nano sheets are actually very large in the XY direction, but they're very, very thin to the point of being a nanoscale material. So in nanotubes as well, they can be very long, so not nano in the length, but in the diameter of the tube they can be. So I think it's important to remember that nanoscale can mean a lot of things, and I think that's also a misconception. Sometimes people assume something is a nanotechnology when it's actually not, and it's a lot larger than the nanoscale. So it's a very broad definition that I think is expanded out a lot over time to things that are not just at the nanoscale, but have an element of nano to them. I was going to share one other, I think, common misconception is that every nanoparticle is bad at large quantities, or a similar kind of notion that the moment we start to aggregate or we have a huge amount of nanoparticles, it could be very bad for maybe our respiratory system or for environmental sort of ecosystems when they accumulate. There's certainly a case where many nanoparticles can be, but there are others that can actually aggregate and do positive things. And a really good example I have of that is our Great Barrier Reef here in Australia. You may or may not know that coral bleaching is causing huge amounts of damage to various environmental areas that are coastal and have lots of coral reef. The Great Barrier Reef in Australia, which is all along the north sort of coast of Australia, the north east coast of Australia, has been experiencing a massive increase in coral bleaching, which is causing a sort of a degradation and slowly decaying of a lot of the reef. There have been many reasons for this, rising sea temperatures, various other environmental factors, but one thing they found expedited it was nanoparticles from various lotions, pharmaceuticals, healthcare, sunscreens, and the like, that have started to accumulate and cause increased reaction at the edge of all of the surfaces of the reef. So in that sense, yes, it can be negative. But interestingly, in the last year and a half, some researchers in Australia have thought that the solution to coral bleaching is actually nanoparticles as well. And they started to find some sort of like lipid-based nanoparticles that can start to coat the outside of the coral, and that slowly helps and prevent it from bleaching. So in that case, starting to accumulate them and aggregate them actually leads to a really beneficial element to the system. So I think we just need to remember how they're being designed and making sure that there's this concept of safety by design in the world, which is this idea that you don't just make something and then figure out how it can be safe afterwards. It's how can we, from the very outset, when we make a material, design it to be safe, kind of build safety into the thing that we're making. And if you do that, I think you can have nanomaterials and nanoparticles that will be very beneficial and safe by their very own nature to the environment. And in that case, accumulation, excess amounts of nanoparticles can actually be a positive thing.
So Dr. Sherman and Dr. Nava-Medina, in a previous question, you mentioned artificial intelligence. And in our Q&A function, which we thank you attendees for utilizing, an attendee mentioned that the 2024 Nobel Prize in Chemistry was shared by 2 AI engineers who applied AI to protein folding, which I think Dr. Nava-Medina, you mentioned also. So we're wondering if you could elaborate on how exactly artificial intelligence is being applied in the field of nanotechnology and nanomaterial research, and if you foresee continued or even greater use of artificial intelligence in the field in the future.
Yeah, so computational chemistry or in molecular biology, like molecular biology is already like getting benefit from like the computational chemistry from years ago, but now you can there are models like that and software that are like completely relying on AI. For example, Schrodinger, which is a software that molecular biologists, physicists, and many other scientists are using to understand, like, oh, how is, for example, a vitamin gonna enter a cellular membrane. And so like they have come up to that point where they are able to predict, like create models to understand that diffusion in the cell. And so this is like this is way beyond what it was like with the computational chemistry of just putting 2 molecules together. The complexity, like the AI is really helping elucidate this complexity and find like give better understanding for how dynamic systems work in general.
Yeah, I can add to that. Sorry, Dylan, if you want, you can go.
No, please, Vignesh, you take it away.
Okay, thank you. So recently, our group, Rain Uline's group in our institute, we published a manuscript where we show that peptide drug nanoparticles. So if you use peptide and if you encapsulate the drug inside as a nanoparticle to around this peptide, it increases the solubility of the drug. The bioavailability will be increased a lot, and it's good for cancer therapy, etc. So to understand this, we have screened several peptides. I think more than 10 different kind of combinations of peptides, and also more than 100 drugs. we have screened, and out of that, only 1 or 2 was successful. So where AI will be much useful is that if we have some lot of information about what kind of molecules can interact with each other and what kind of properties we'll get out of it. If you feed all this data to the existing AI, I think in coming future, we don't have to struggle in lab for this many trial and errors, in which case more than 80%, 90% we fail. And we lose a lot of time. We spend a lot of chemicals, we spend money on that. But I think in future, AI is very promising tool. Based on existing data, it can predict very accurately what is going to work and what kind of combinations you will have to try. So it can suggest us best solutions based on existing data, so that it will save a lot of time and money. That is one of the important advantages, I think.
I can probably very quickly add to that. One final application, this is very practical, that I found AI and sort of machine learning data to be useful is you don't get a lot of data sometimes to understand the nanoscale. So there's a technology, an instrument called crystallography in science, which allows you to understand the crystal structure. So the arrangement of atoms in a particular structure. That relies on X-rays, which are quite large relative to the nanoscale and nanoparticles. And there's only so much data at the nanoscale you can collect using crystallography and other techniques that allow you to understand structure and organization of a material. So using AI and using modeling allows you then to start to get different data that you can compare to what you see experimentally. And sometimes there you can kind of link the two together and fill in the gap that you can't get experimentally and go, well, if this is what the simulation says and we see this slight blip or variation in this data here, then together we can hypothesize that that change is happening because of what we see in the model. So it's a little bit of a way to uncover things that we can't see experimentally because we just don't have the technology or the insight at that resolution to see the nanoscale, and then link up observation with theory to be able to conclude what might be happening at the very small scale.
Okay. Next question is one that's certainly popular among future problem-solving students, and that is, what ethical issues come with the widespread use of nanotechnology in the future? How can we tackle them?
I can start with the idea that I think anything that is too small to see becomes very difficult to regulate and manage. An analogy, this is maybe not the closest analogy, but an example is when we all started to move online. And all of a sudden identities didn't have to be your true name or your true face, and people could start to hide and come up with fake identities, and all of a sudden you didn't really know who was who, and sort of the risk of identity theft or the risk of being anonymous when you interact online increased a lot. When you have large pollution, let's say you've got an oil spill in the ocean, let's say you have any other kind of pollution that's going in the streets or in the forests, you can see those and you can manage them and regulate them, but nanoparticles are not visible and are not as easy to detect in various other areas, which makes it a difficult question as to say, well, how do we accept, how do we reject certain nanoparticles, and how do we make sure that people are safe and comfortable using these in a way that makes it all right? So I think for me, one of the biggest ethical issues is for something that's so invisible and something that people can't see, how do we make it safe and comfortable for people to use, and don't risk having these things being turned into weapons or into, and I don't mean weapons necessarily physically, they can be anything used for nefarious intent, things that may be able to surveil without people realizing, or may be able to slowly pollute without realizing, and those sorts of risks. So that's not nanotechnology alone, right? It's any technology and how it can be used for good or bad. I think on the whole, though, there's maybe less risk of that than we might think with nanotechnology, and that may be a little bit of an illusion that's built out of a lot of science fiction and our nanobots taking over the world, which is not maybe the point that we're quite at yet.
Ilse, you want to tell something about this?
I think I resonate with a lot of the biodegradability. There is like I early on, like Dylan mentioned, like okay, you wanna design something and then you wanna see what's gonna like really think through the fate of it, and that includes like studies for like leaching that some of the new products out there might never look at how it decomposes on the soil or how degradable it is. So I think that those two, yeah, it's just like complementary to what he has mentioned. Yeah, I think that is those are big concerns that or the concerns exist, but I think they're often overlooked by how the companies work, large corporations particularly. So just like the message here is like to always think through, like as many of you the students here like are thinking of new ideas, to always keep that ethical side in throughout their careers. So
Yeah, I also agree to the point. Everyone is not very honest. So for commercial needs, for business, people hide a lot of things. So for example, everybody use most of the people use sunscreen. So people don't think how it's going to work, no? So it takes light, and what happens to the light? So sometimes, most of the time, the light which is absorbed, UV light which is absorbed by sunscreen, that is converted to radicals. So after long time use, definitely it can cause cancer. So, but nobody tells about that. But some companies definitely they take precautions. They have some other molecules which can quench these radicals, and they ensure safety. But not all companies do that. So the hidden truth about the health hazards, always that is an ethical issue, which we can see. The solution for this could be, I think scientists have to take the lead. So when they publish or when they give presentations, they should be giving more awareness to the public about how to use the material, and don't overuse and don't overlook at the features and the use of that material. So I think awareness has to be created.
So we've touched a bit about the possible dangers of nanotechnologies and nanomaterials, but what are some major challenges facing the research and the development of nanotechnology in the field?
Want to go first, Dylan?
Yeah, I'm happy to start. I think sometimes this is maybe a broader research discussion. Sometimes research is limited by seeing direct application and relevance of research, and then therefore having the funding and the opportunity to be able to do the research. More and more, there's a lot of areas that become really popular, and therefore funding moves towards that, and it becomes easier to do that research. At least my experience has been in nanotechnology and nano work, unless it's directly related to a big global issue, unless it's related to something that really needs action. Sometimes finding funding, sometimes finding the ability to do the research can be quite difficult. And there are elements of nanotechnology that's highly experimental. And when things are so experimental and so far from reality and making change on impact, it can be difficult to get that. So that's a practical, I think, practical issue or limitation and challenge is how do we keep the funding, and how do we drive interest in something that can also be sometimes a bit far away from application, and also has some negative connotations in certain ways. Generally, I think another challenge is always commerciality. It's very easy to make nano things in small scale in a lab in a controlled environment, but to scale that up and make enough of it to be able to produce a product and release it and keep the quality and keep the quality assurance of the product that you make at that large scale is really, really difficult. And it's often what limits a lot of growth and development of materials that are at the nano level from things that I've experienced so far in research.
Yeah, when you talk about research in nanotechnology, what I felt is that the main problem comes with the sensitivity of the material and the process which you use. So very, very sensitive to all factors like environmental factors or your human skills, everything. So many times you will do small mistakes and many things will go wrong, and it may not work again. The reproducibility issues, they are much more higher in nanotechnology field compared to other field of research, I felt, because of the sensitivity. It's very, very sensitive. So we should be very careful and the vigilant and patience, patience, everything is required when you do research in this field.
Okay, thank you both for your insights. So I believe Dr. Sherman mentioned earlier that the nanotechnology industry is quite hard to regulate. So one question that we had from students was, how is nanotechnology being regulated? And in what ways are these regulations working well or causing issues such as hindering research developments?
So this varies significantly depending on, I guess, country and depending on region and jurisdiction. I know alone in Australia that we have 7 different government and sort of private bodies that regulate nanotechnology. It's surprisingly, I think it's surprisingly more regulated than you might think it is. So just in labs and research alone, you often have to undertake training and you need to get approvals to use nanomaterials in any lab in the world. And that's just the first step if you're doing research. If you're then going to start to try to commercialize or release nanotechnology, you have huge amounts of trial, paperwork, expectations to justify that the material is going to be safe, at the right kind of standard of quality, and will do what it says it's going to do. There are then measures of how much nanotechnology, so the mass or the quantity being used in certain materials, and that's carefully controlled and managed as well. So I think it's a surprisingly well-regulated industry in terms of where things stand. But that's Australia. I can't really speak for the rest of the world, but in many ways it's regulated kind of like every other dangerous material is, and it's about the quantity of use, making sure that it's safe and secure and it goes through trials before it ever gets out into the real world.
Yeah, if we want to talk about whether this kind of regulation hinder the research, yes, it happens, because the rules are created by people who don't understand or appreciate science. They just look at the safety measures. So, for example, I will tell you as an example here at New York. Now we got a regulation that you cannot use dichloromethane in laboratories to synthesize. So if researchers, if you think about that, without dichloromethane, I don't think many synthesis protocols will work. This is a very important chemical for us to do some synthesis. So the people who made the regulations know that this is a very harmful solvent. Yeah, so it can cause cancer if you are in exposed to the solvent for a long time. So they focused only on that point and they created a regulation. But what will happen? How we will do the research? So the solution for this problem, that a chemical is harmful, so you don't use that is not a solution actually. So the solution should be like, we should be given awareness on how to handle the chemical. If a chemical is harmful, there are other ways to use that chemical. So instead of having some regulations to give some restrictions without thinking about the use of that chemical, if we just take some regulations, that's not going to work like that. So I think we have to, there should be more awareness about these kind of regulations, and the people who provide this kind of guidelines, they should understand and they should find some alternatives so that they don't hinder the research. That's my opinion.
I can probably quickly build on that and say that because we don't exactly know the long-term effects of some of the nanoparticles, generally governments are being on the safer side of things because they don't want to lead to the potential risks being eventuated. So often regulation is more cautious than maybe it needs to be because we're not sure yet of the implications. So in many ways, we need more data. We need more understanding. We need a bit more unity around the world of what we mean by nano and nanoscale and particles to be able to move forward with, I think, improved regulation that aligns with what is needed for innovation and development.
Thank you. So I know before during the question on the ethics of nanotechnology, the environmental impact of it was touched on, and that's a big thing that our attendees are wondering. So we were just wondering if you guys could elaborate on what effects nanotechnology and nanomaterials have on the environment, and what is it that causes these effects?
Dylan, you can start.
Yeah, sure. I'm going to start with a positive story. So I think nanotechnology can be very good for the environment. We have a large agricultural industry in Australia, and nanotechnology is being used within that to be able to protect a lot of our crops from particular invasive species or insects, and particularly drought as well. So finding ways to uptake water at a faster rate than what might otherwise be able to be achieved, or being able to help it resist the huge amounts of UV that we have in Australia that irradiate from the sun, because of one, we're missing ozone, but two, we're just on an angle that's a lot closer to the sun than the rest of the world sometimes. So in that sense, there's a lot of opportunity there to be able to do good for the environment. There's also, and this is just a really fun fact, I think it was late last year, someone's discovered the first ever biodegradable glitter thanks to nanocrystals. So now when you go to parties and you're out there having fun in the world, if you throw glitter out there, you know that you don't have to clean it up and put it in the bin, because it will, it'll degrade itself over time. And that's thanks to having these very small nanocrystal particles that under UV are going to be able to break apart a lot more easier than these larger, clumpier materials that used to be, well, they are plastics that used to make a lot of the glitter material. So in that sense, there's a lot of good there that I think nanoparticles to do with making things more biodegradable, more environmentally friendly, as well as being able to support and strengthen elements of nature. The materials I've worked on have been used for water filtration and water purification. So at the nanoscale, we can start to absorb and desorb certain toxins within waterways and make sure that we can keep water quality at the best level possible for consumption. And our sort of devices we're looking at were particularly in urban areas where there might be a lot of water plants and filtration already there established. So in that sense, really, really good things that I think can happen. As always, there are negative repercussions, and a lot of these, I think I mentioned the Great Barrier Reef earlier, where you can have particles that you don't expect nanoparticles to necessarily be a problem, but as they start to accumulate in the environment, basically, I'll go back to what I said right at the beginning in the first question, which is that nanoparticles have more surface area, and that can increase the likelihood of them interacting and reacting with other things. And then you get something called a radical, which is a very unstable, I guess, piece of matter or material that's likely to react with other things and react with other things. And then that's going to cause a breakdown or degradation of material. And it's these increases of free radicals and the increase of other kind of chemicals at that very small level being kind of encouraged by or catalyzed by the nanoparticle that often then causes this breakdown. In humans and animals, it may be increases of risk of cancer, and then slowly a little bit more damage to the environment. But I'm probably more pro than I'm negative, although I very much understand and appreciate that there's a lot of risk there as well to our environment.
Yeah, I also agree completely to your thing. So the positive things are much more useful and unavoidable compared to the negatives. But the health hazards, we should be very careful. For example, nanoplastics. In many food items, we can see this is creating a big issue nowadays. But when you see the positives of that, I think we should find some solutions rather than stopping the usage of this kind of technology. So definitely we have to do some research on reducing the hazardous effects. Yeah, that's what I also felt.
Okay, so I'm looking at the time and hopefully we can get through one or two more questions quickly. So one question I was also seeing in the Q&A function is, where do you see the field of nanotechnology in 10 to 20 years? How will it change your daily life?
Yeah, I felt that current nanotechnology mostly that is focused on biology and medicinal field. But I think in next 10 years or more than that, we'll be seeing that more into the day-to-day materials. For example, long time back, we see this much big computers. Right now, it's becoming a very thin sheet, and laptops, very lightweight laptops, etc. So why can't we build some useful material? For example, if you take cell phone, in future we have to see it's non-chargeable cell phone which can charge by itself. For example, we have watch like quartz watch. When you shake that, it will charge by itself and it works. Why can't we build a cell phone which can charge by itself when you just walk? So if charge is gone, just go for a 30 minutes walk. It will work for 2 hours, 3 hours. So these kind of innovations, I think we have to think. We have to bring this kind of very useful things, and also more care should be taken for the environmental hazards. Because population is increasing, we are using all the kind of technology which creates huge amount of waste. I think in next 10 years, more focus will be there on how to reuse the materials and how to get rid of all this kind of waste. I don't know, Dylan.
Yeah, those are great ideas. I agree completely. The idea that nanotechnology is going to be more integrated into our materials. You think about any kind of new material, plastics, for example, that once was a very new idea and just formed, and then very quickly now it's in every second material that we use. So the idea that it's becoming more accessible and more integrated into other materials is a really big point. The second is simply price. I know carbon nanotubes have dropped from $1,000 to something like $50, from somewhere between 2005 and 2015, I think. So that's a huge decrease in the cost that it would be to use that material. And if you think about now that's not linear, that's a bit more of an exponential curve we're seeing on price reduction. And I think we're going to keep seeing that reduce and reduce more and more as we do the research. And maybe one example just to finish off, this is very future problem solving. This is probably an idea I would have once dreamed of writing in step 3, but now it's actually a reality. There's something called a triboelectric nanogenerator, a TENG, T-E-N-G. And it's a little bit about what Vignesh was saying. It's the idea that when two materials get very close to each other and rub next to each other, it can create energy. And sure enough, there are people that are starting to build models in the lab of the idea of these TENG-powered exercise gear or shirts. And if you can put TENG within the fabrics of a shirt, your mobility from running will start to potentially power your phone or power your device. That's a little bit blue sky thinking, but it's there as a concept. And I think that before we know it in time, something like that, 10, 20 years could become more practical. And if there's someone out there that wants to make a business and is ready to invest, they could very quickly, I'm sure, have a very exciting and successful product making positive difference to people's lives, which is at the end of the day what the aim is to do whenever we're researching and building technology in the lab.
Might be an extension of the smart clothes topic we had a few years ago. We'll have to let the topics committee know about that one.
That was our final question. So I'd like to thank all of our attendees for coming, everyone who utilized the Q&A function, and everyone watching the recording. On behalf of the entire future problem solving community, I'd like to extend a huge thank you to Dr. Sherman, Dr. Athiyarath, and Dr. Nava-Medina for their time and insights today.
Thank you, Trevor. Before I conclude, I'm going to turn it over once again really quickly to Vedika and Mahi to talk a little bit more about the Future Problem Solving Student Advisory Council.
Hi, everyone. We'd love for you all to be a part of our mission. We've done a lot of amazing work, and we're still accepting applications to the council, and anyone over 13 years is eligible to join.
Just to give a quick overview of what we do, some of our current projects include outreach, sharing insights from students for students. So future problem solvers around the world can get to hear from other students or maybe more experienced problem solvers. We're also working on free materials to support future problem solvers, the first of which is a guide to GIPS, if that's something that interests you. And of course, these amazing research panels are something that we'd love for you guys to have the opportunity to contribute to. Speaking of which, our research team has been brainstorming something unique. Trevor, Cyrus, Brianne, would you like to take just a couple seconds to talk about it?
Yes, of course. So we've seen a lot of questions on the 6 steps of the GIPS booklet. And we're actually working on a panel for the Global Issues Problem Solving booklet. At this panel, we plan to host evaluators, FPS alumni, and more to discuss how we might approach the booklet steps and improve our writing. It's not a confirmed panel yet, but please keep an eye out for updates and announcements on this.
There'll be an email in the email we send out after this, Student Advisory Council, fpsbi.org. If you email it, you'll receive an application to join. If you have any questions, feel free to email us about it as well. Once again, thank you so much to our panelists for taking time out of their day to talk to us, and thank you to everyone who attended.
Thank you so much, Vedika, and thank you for sharing the opportunity. This time last year, we were just starting with these panels, and now it's a regular part of our offerings to our students. And I'm just so pleased and proud that the ideas that our youth are generating are making all of our programs stronger. And I encourage you to keep brainstorming on ways to keep doing that. So thank you so much to our panelists and to our youth leaders. We wouldn't be here without you. I hope everyone has a great rest of their day or evening, wherever you might be.
Thank you, everyone.
Thank you.
We'll see you later,
Thank
and
you.
good luck with the future problem-solving scene coming up on nanotechnology.
Thank you.
June 4th. Oh, no. That's the conference. Sorry.
No, that's something else.
Nanotechnology is coming soon in March and April to most of our students, and then in October for our Southern Hemisphere problem solvers. Thank you so much.
Okay.